Let us finish off with the Huffman coding then, which was left. Because this is a very common and a very useful source coding technique as far as Huffman is concerned. So I'll write this. Because you will definitely have one question both in Cat 2 as well as for your term end from this particular segment of Huffman coding. So it's a very important part. Like the one that we have done for Shannon binary as well as Shannon Fano, Huffman coding has its importance till now. Because both Shannon Fano as well as Shannon binary, they are very obsolete, a bit old actually. Whereas Huffman coding, rather the adaptive Huffman and all, they are still being used in many of the applications. So that's why the importance of this coding is there. So before going to the problem itself, we are going to do some of the steps like we did for the other coding. So the first step is the source symbol symbols are listed in the order of decreasing probability. So it is very similar to what we had for the other codings as well. So whatever the probabilities are given to you, you have to make sure that the highest one sits right at the top of the probability chain and the last one will be the least probability. So that's one. Second, the highest probability is always denoted as 1. That is after the splitting part, like at the end when you are reaching a position where you only have one element in the series, like we already did. So the highest probability will be 1 and the lowest probability will be 0. So just like in Shannon Fano also we know it, so that's why I'm not looking into this, because the process is something very similar to Shannon Fano. The third point is a new source symbol with probabilities equal to sum of the original probability is calculated. We'll see with the numerical, this is only the steps. The probability, this is where it is important. This is where it differs from the rest of the coding. The probability of the new symbol, is placed in the same list such that the order is maintained. So what does this mean? that by adding up with two different probabilities, if we come across a new probability, it will be placed in a position so that the order is maintained. Either there are two methods actually, minimum variance and maximum variance method. In both the cases, you will observe that whatever happens, the new element will be placed in a way such that the order of decrement of probabilities or the order of increment, whatever you call it, with both will be remaining as is. Okay, so the new probability should not violate the order in which the probabilities are placed. That's the main important part. Now let's see another part which will end. So just like we had calculated the efficiency and the redundancy of code, same goes for Huffman coding. We can also calculate the same. So that's nothing new. The only thing that is new in this case is fourth one. A measure of the variability of code word length. The measure of the variability of code word length of a source code is given by V as a summation of k equal to 0 to k minus 1 P of k LK minus L average whole square, where Pk is the probabilities of the original symbol or the original source which is having Pk number of symbols, probabilities. Lk are the individual length and L average is the L average as we all know. This is average code word length. So probability of the kth symbol multiplied by within the square Lk minus L prime. So that is what the idea is. So we have to calculate the variance. This variance thing comes only during Huffman coding. What is the calculated variance for the code? It will come. So ideally, before in source in Shannon Fano as well as in Shannon binary, we have calculated the redundancy, the efficiency of the coding. Okay. Along with that, now for Huffman, along with those two, now a variance in the coding will also be added. So for given numericals on Huffman, you have to calculate the variances. So let's take an example and we'll solve one by one. It's very simple, yet if you mistake in any of the step, complete segment will be wrong. So be very careful. We'll take a smaller example and then we'll go ahead. So the first thing is called as the minimum variance method. So the first thing is minimum variance. So by this variance, what we mean is that from the effective code word length will vary in minimalist way when we are using the minimum variance method. That is the idea. Okay. Now the process is we have 5 set of symbols. Let's have x as given as x1, x2, x3 and x4. X5 also there. X5. So we have 5 symbols, each having a probabilities P 0.4, 0.2, 0.2, 0.2 and 0.2. This is 0.1 and this is 0.1. So 0.4, 0.2, 0.2, 0.1, 0.1. So these are the respective probabilities. Now the first step anyway, as you might be aware, it's already in the order of decrement. So the first step is anyway done. If it is not done, then you have to rearrange the probabilities so that they are all in the descending order. That's one. Now we will write in this way. So first we will write symbols or the probabilities P of k as 0.4, 0.2, 0.2, 0.1 and 0.1. Then see the process I am doing. Okay, we'll take a bigger example after this. We'll write here code, but we'll not write anything. But after this column, we will again write pk, because the rule is you have to pick up the least two probabilities present, because you are already arranging it. The least two probabilities present, add them up and find the new symbol probability. Because you can see the third point, I think we have referred to that. So the process is, and we are looking at minimum variance method. So the process is that we will add up these two, because these are the two least, we have to add these two, and we will put it on top of the other existing element. Like for example, what is the added value? 0.2. Now 0.2 is already present over here. But for minimum variance, please make a note. The 0.2 will always come on top of the existing two elements. So what I'll do is, I'll make a mark with this green color so that you can understand this 0.2 is the one that has been added. So this is 0.2 actually. So 0.2 is generated by adding up these two. The placement is where minimum and maximum varies. This for minimum variance method, if it is asked to find out, 0.2 will come over here. In maximum variance, if the opposite way around, it will come at the bottom. Simply as that. That is the only difference. And you can keep 0.4 as it is. Clear with this first step? This will be followed, the same process will be followed until and unless each of the probability column will only have one element. Right? So, again, we'll write this. We'll have a code here. We'll keep it blank. Can you tell me the orientation of the third segment? So here, the last two segment again we have to consider. Okay. So again, if I consider this 0.2 plus 0.2, it's 0.4. But since it's a minimum variance method, we will put the resultant value on top of the existing 0.4. Right? So 0.4, I put a green color here. Then I go back, I will keep this 0.4. I will keep this 0.2. And see, the two elements which we have already taken, we are not writing that once again. Because the sum of this, we have already mentioned. Clear? Again, code. It contains three elements, hence we can add once again. So the next set of probabilities will be adding up these two, which is 0.2 and 0.4, which is 0.6. And this is naturally higher. So you are keeping this as here and 0.4 as here, and you are marking this as a green. Now, making this color is not important. It's just for the time being, since we are doing it for the first time I'm doing it. You can neglect that doing, but keep a track of where it is being generated. Because you will soon find that it creates a lot of problem at some later stage. Now I'll go here. I'll put the code here. Right? Now you go to the fourth law. I think in the fourth law it's mentioned, or the first one I think, that keep the higher probability as 1 and the lower probability as 0. Other way around is also possible. You can keep the higher probability as 0 or the first one as 1. What I have mentioned here, 1 and 0. Okay, this is what I have mentioned. The higher probability to be 1 and the lower as 0. Make assumption, just change it to 0 for the time being. It can be other way around as well. We are doing in this way. We are keeping the higher to be 0, the lower as 1. Just change it for the time being. It's very similar to like we did in channel fan. It's the same thing. You can go ahead doing it. So what we are going to do is, we will put 0 over here and 1 over here. Simply. One bit, 0 and 1. Now the trick is, we will go backward. So 0.6 is generated by these two. So 0, 0. But since 4 is greater than 2, we will put a 0 over here and 1 over here. Check this step. We are first making sure that there is no other elements to add up. Why we stopped here? Because 0.6 and 0.4 will give you 1. And that doesn't make any sense. So we will stop at 0.6, 0.4. Now the rule is to make this as 0 and 1. Which I said, it can be other way around as well. 1 and 0 can also be a process. So 0 and 1. Now 0.6 is generated by both this 0.4 and 2. So first we'll write 0, 0, and amongst these two, 0.4 is greater, hence we'll put 0, and this one is 1. Whereas this 0.4 has come from this point. Okay, so it has remained unchanged, so 1 will remain as it is. Can you finish off filling the gaps coming from right to left? And can tell me each and every step what are the codes you are getting? From right to left, you check the particular new element being generated by which two probabilities. Give the same code to that, along with check which one is greater. And if they are equal, then naturally treat the top half to be 0, the lower half to be 1. That's the simplest thing. So, sir, because this 0.4 is nothing but this one. Yes, we are going back calculating, right? So this was 0.1, that's why I have written 1. Now, 0.4, this 0.4 is now generated by this 2. Okay, come back here in the next column. 0.4 is generated by 0.2, so we will put 1 and 1 here. But since 0.2 is top half, so we'll put 0, we'll put 1 over here. Whereas this 0.4 and 0.2 are coming from this point, from the earlier half. So this 0.4 is coming as 0, 0, whereas 0.2 is supposed to be 0. I'll repeat once again. First half we have 0, 1 at the right hand side corner, 0.6 and 0.4. Now 0.6 is generated by the addition of 0.4 and 0.2. So since 0.6 has code 0, we will initially put 0, 0 on each and every element. Now amongst those, the one that is top half will be given as 0, since that's the way we are doing it for all this while. So we have put 0 over here and 1 at the lower half. 0.4, since it has come from here, it will remain 1 as it is. Now just before to this 0.4 and this 0.2 are the positions over here. So they will retain their code 0, 0 and 0, 1. Whereas the new element was formed by 0.2 and 0.2. So all this will have 1, 1, but the top half will have 0, the lower half will have 1. Am I understandable? Is it fine? We'll solve another one. No problem. For the timing, see whether you understood. Can you give me the next half? The last of the column which is left. Okay, let me just put it in some other. 0, 0. Very good. Then 1, 1 or 1, 0? Okay. Next. Very good. Simple as that. The only thing is, the formation of the source coding is different to that of Shannon-Fano. First of all, it's very quick. Compared to Shannon-Fano, you are taking less steps to find out. Second, there is a saving of number of bits. And you will soon find that the efficiency of the coding is also very good. Can you find out the variance as well as the efficiency and redundancy for this code? Please do it. Understandable? We'll take another example. We'll soon find that this process will be a bit cumbersome at some point, because when you have more number of probabilities which are very equally likely happening to happen, like 0.001 or something like that, is very less, then you will find there will be an issue with the process in which we are doing. So for that, they have another process or extended Huffman coding, we call it. We'll see that. First, we will solve this. Please try to solve for efficiency of the coding, the redundancy of the coding, and the variance that we had the formula. Again, as I told you, you can change the order of zeros and 1 at the end. That is, this one you can either opt for 1 or 0. The code will be the word will be different, but the length and everything will be the same. Combination of words will be different. But that doesn't affect our efficiency or anything of that. Because anyway, what is the combination of zeros and 1 doesn't matter. Anyone the answer for it? I'll go one by one. Can you give me L average? Okay, 2.2 bits per symbol. How many of you have in exam omitted or left the unit to me to understand? Just while writing, I thought of one thing. How many of you have not written anything in the unit? Raise your hand. Sir, we don't remember anyway. Okay, entropy. HS? HS? 2.12 12193. Okay. I'll put everything. Okay. So we have L average, we have HS. Efficiency can be calculated as HS by L average. Coming around? So this is the efficiency for the coding efficiency for the given set. Now, can you give me the variance? Variance has the formula P of K, LK minus L average whole square summation. So substitute the respective probability. You only have to take the last one, because the last column, rather the first two columns are the ones where you have to highlight. See, this is what you have to focus on. Only this one, because the code that you are looking at over here, the first column, second column rather, that is your final outcome. So for the corresponding probability and the respective LK are the bits. Like in case of first bit, it is first probability is 2, second is 2, third is 2, fourth is 3, and the next is 3. So LKs are given by that. L average is anyway you have calculated as 2.2 bits. Take the square of it, multiply with the respective probabilities. .16 is the calculated value. Okay. So this is my variance. This is a variance. So we'll keep this as an example. That's the first thing we will do. Now use the same process for the same given problem. Wait. For the same given problem, use it for maximum variation. So maximum variation, what you will do is, I'm not telling you what to do. You add up the two elements at the end and you put it at the bottom of all the elements, keeping the order of probability same. You understand what I said? You add up the two last element, whatever be the value, keep it in a position so that the order in which the probabilities are placed remains as it is. It should not disturb the descending order of probabilities. So, can I form the table for that? Let's see. I'll also do it. So, we'll go on a new page maybe. So again, we have symbols which are x1, x2, x3, x4 and x5. The probabilities are given by 0.4, 0.2, 0.2, 0.1 and 0.1. We'll keep the code part as it is. We'll go for probabilities once again. So what I asked you to do is, you add up these two. So this is maximum variation we are doing. So this is maximum Huffman coding or maximum variation Huffman coding. Maximum variance of Huffman coding. Okay. So what we are going to do is 0.1 and 0.1 we'll add in the same manner like we did, but we will place at the bottom. So 0.4, 0.2, 0.2. So this is same. So the new element, if I mark it once again, is placed at the bottom of the tree. Okay. Now, in case of minimum, we had put it on top of it. So that's the only difference. So if this is the process to be followed, fill up the whole table, find me the code words and the respective calculation. You do it, I'll also do it here. So 0.2 plus 0.2 will be 0.4, but it will be placed below this 0.4. So your 0.4 is here. The new 0.4 should be here. I'll mark it. So you have taken this 2. So the left is 0.2. So we'll put it over here. Code probabilities. Again 0.2 and 0.4 is 0.6. See here at the last step, when you are adding 0.4 and 0.2, it is becoming 0.6. But 0.6, if you put it less than 0.4, as per the maximum variance method, what I'm saying is, suppose you put it over like this, 0.4 and 0.6. If you put it this way, as the maximum variance will tell you to substitute at the bottom, the orientation of the probabilities is violated. It's not in the descending order. So, at the last step, you always need to place in the order in which we are supposed to put it. So, we'll have 0.6, we'll have 0.4. So, I'll just remove this one. Can you find me the code for now? Again, follow the same trade. The upper half will be given 0, the lower half will be given 1. We'll do together. At the last step, we have 0 and 1. What are the codes before this column? Last but one column of code. This is 1. Then is it fine? This 0.4 is remaining same as it is. So we can keep this as 1. We can keep this as 1. This is, you can do it individual steps as well. But ideally 0.4 has remained unchanged. So we can keep that 1 as it is. This 0.4, so we have here 0.4 is generated by this 2. So 0.4 is given by 0, 0, 0, 0. Now this is the top half, so we'll put another 0. Lower half will be putting at 1. This 0.2 is unchanged, so this will be remaining as 0, 1. Okay. Now this part 0.2 as it is, so 0.01 here. This 0.2 remained as it is, so 0, 0, 0. This lower 0.2 is a generation, so this will be 0, 0, 0, 0, 0, 0. Ideally this is 0, this is 1. Oh, sorry, very good. Right. This should be 1. So, correct. So basically this is how you have to perform in case of the maximum variance method. If it is mentioned as minimum and maximum, you have to do both. Ideally any one is suited, but you have to mention which method you are following. So can you quickly find out what is the efficiency of the coding? Quickly, just the efficiency. It's coming as same. But can you find the variance of it? The value is coming around 1.36 compared to 0.16 which we got in the other case. Remember this V, the variance is coming around 1.36, whereas in this case the V was 0.16. So the variation in the code words are much lesser in case of the first half in this. Whereas in the second case you are observing that there is a lot of variation. You can see 1 bit here, 2 bit here, 3 bit, 4 bit. All the code words are different in length of it. Whereas in case of minimum Huffman coding, all of them were mostly of 2 bit and these were all of 3 bits. So the variation is comparatively less. That's the idea. So now if I give you one example, a little bigger. So let's hope you can solve it. So we'll drop the question here. A long sequence of symbols is generated from a source and is seen to have the following sequence. Don't write everything. Sequence. The sequence is something like this. Symbol and occurrence. Symbols are A1, A2, A3, A4, A5. Occurrence are 3003, 996, 2017, 1487, 2497. So a given source is generating symbols where the symbols are occurring with this particular rate of occurrence. Assign a Huffman code. The question is, assign an Huffman code to the above symbol okay. Also calculate the entropy, average code word of this particular code, and third, calculate the efficiency of the code. A long sequence of symbols generated from a source is seen to have the following sequences given by the table. Assign a Huffman code to the above symbol. Also calculate the entropy, the L average, and the coding efficiency. So probability given was numbers. So what we have probability we cannot really go ahead with the Huffman coding. So how to calculate the probabilities? How to calculate the probabilities? What is the probability of A? Probability of A1. It's nothing but the number of time it has occurred divided by the total number of occurrence, which will come around 10,000. Okay? So find out the probabilities, arrange it in order. first day will give up this. We have done the cat question right now. We all know what he is about. And after that, we add the MCQ. We have surveys, 3 to 4. I will change this. Mostly they will follow the minimum Huffman minimum variance only. So even if nothing is mentioned, just go ahead with the minimum. Yes, that's a must. The order of the probability in the descending order is a must. In each steps, whenever you are writing the probabilities, it should be maintained. Otherwise, it will violate the rule of any process of source coding. Ready with the solution? Okay, first thing first, give me the probabilities of A1, A2, A3, A4, A5. So P of A1, probability of A1, 0.3. Probability of A2, point 1. Yes, 0.1. I'll give it 0.1. A3, 0.2. 0.01. No, I'm asking PA3. PA4. 0.15. We'll take it approximately 0.15 here. PA5. 0.25. So is the order correct? In the way, so the order should be A1, A5, A3, A4, A2. So the order should be A1, A5, A3, A4, A2. So A1 is given by 0.3, 0.25, 0.2, 0.15, 0.10. So this is one numerical where actually the order was not given directly. So you have to find out the probabilities and you have to arrange it in the correct order. Give me the probabilities over here, one by one, from top to bottom. Give me the probabilities from top to bottom. Probabilities, not the code. Point 0.30, okay. So this will get added up. It is 0.25. It will be on top of the existing 0.25. So your 0.25 comes here. I can make a circle so that I can understand properly. I'll make a arrangement like this. Then this 0.25 comes in. 0.2 remains as it is. Now this 0.25 and this 0.2 gets added up. So this is 0.45. 0.45 is greater than 0.3. So we have to carry on in that manner. So it will be on top of the chart. 0.45. We will circle it. Then we'll put the ordinary ones. 0.30 and 0.25. Anything else left? No. So now we will add up 0.30 and 0.25. That's 0.55. 0.45 comes over here. That's correct, right? Now give me the code one by one. First is naturally 0, 1. So second will be. So give me the codes from top to bottom. 1. People from that corner. 0, 0, 0, 1. Okay. Next code. 0, 0, 0, 1. Last column. What is this? 0.25. Which one? 1, 0. 0.2. 0.15. 0.15 and 0.10 has generated 0.25. So 0, 1 will come. So these are your codes. Now you calculate the efficiency in the same manner and you get the solution. I'll give 2 tasks for you. Tomorrow when we are coming back, just give me the answers. Okay. One is, given the probabilities, just practice this, okay. X as, I'm giving just a probability, 0.3, 0.25, 0.15, 0.12, 0.1 and 0.08. Given this set of probabilities for the set of source X, find the Huffman code average. So calculate the efficiency, L average and the variance, along with find the redundancy. So that's one to do. This is to do. And the other one is, this might be a little tricky. You given a symbol X, this is problem number 2 actually, 1. Given X as X1, X2, X3, X4, X5, X6, X7. So 7 symbols are there. And probabilities as 0.1, 0.05, 0.04, 0.01, 0.04, 0.06 and 0.7. Find the code words HX, efficiency and redundancy. Find HX, that is entropy, L average, efficiency and redundancy. Please try back home, just do both of these problems, because this is sufficient to do for the Huffman coding. But the numericals, the type of numericals, you can expect the first problem that we did. Given the occurrence, find the probabilities, rearrange it and then solve it. It will come in that way. Okay, so practice more problems like that. Online also you will get a lot of problems like that. Just search for it. But these are the techniques. The technique remains same as this. Okay. Thank you.